Welcome to this session on adversarial perturbations. I'm Harry, and today we'll explore one of the most intriguing and dangerous threats to AI systems. Adversarial perturbations involve small, often imperceivable changes to input data that can trick models into making incorrect predictions. This subtle manipulations can reveal vulnerabilities in AI systems, compromising their performance and security. Throughout this presentation, we'll dive into the motivations behind these attacks, techniques used, real-world examples, and effective mitigation strategies. Understanding adversarial perturbations is essential for anyone developing, deploying, or managing AI technologies in critical industries. So let's get started. So what are adversarial perturbations? These are going to be often small, imperceivable changes introduced to the input data that AI models will be ingesting and will be deceived into making incorrect predictions. These subtle modifications are designed to manipulate the model's behavior while being unnoticed by human observers. The core idea here is that even slight adjustments to the input data can disrupt the model's performance, revealing its vulnerabilities. By understanding how these perturbations operate, we can identify risks that they pose to AI systems and mitigate their impact on security and trust. Adversarial perturbations are used for several key reasons. An attacker might be motivated by the desire to manipulate predictions, bypass security mechanisms, or degrade the model's overall performance. In some cases, the goal is to undermine trust in AI systems, especially those deployed in critical industries like healthcare, finance, or transportation. Additionally, these attackers can be leveraging weaknesses in AI models to sabotage competitive systems. And this overall highlights the need for robust defenses. The primary objective of AP is to introduce misleading predictions, where the model's going to behave in unexpected ways. Attackers aim to degrade the system's accuracy, causing it to perform poorly in situations where precision is going to be essential. Another objective is to undermine the trust by exposing vulnerabilities within the model, leading users to question the system's reliability. Some attacks are specifically crafted to bypass security, rendering protective measures like malware detection or facial recognition ineffective. Each of these objectives poses significant challenges for maintaining the integrity of AI-driven applications. So let's go into some of the techniques that attackers will use when trying to employ AP. One common approach is going to be gradient-based methods. This is where the gradients are analyzed to find the most effective way to fool the model. Optimization algorithms are also used to craft minimal perturbations that cause misclassification without raising alarms. Some attackers rely on black box attacks, which involve testing the model without any success to its internal parameters. Conversely, white box attacks take advantage of full knowledge of the model's architecture to design highly effective perturbations. These methods highlight the diverse way attackers can exploit AI systems, whether or not they have access to the model's internals. So now let's look at some more of the advanced methods. More advanced methods include Fast Gradient Sign Method, or FGSM, which will generate adversarial examples with efficiency and speed. Projected Gradient Descent, or PGD, defines the process by iterating to create more robust perturbations. There's also Carlini and Wagner, or the CW attack, which is a highly effective at ensuring the perturbations remain small, imperceivable, while achieving the desired misclassification. Finally, universal adversarial perturbations extend across multiple inputs, demonstrating how these attacks can generalize to defeat these AI systems and deceive different data sets or systems. There will be another video highlighting that will go more in depth here. There's just so much information with and detail with these attacks and sophistication with these attacks that one video is not going to be enough. There'll be individual videos for each one, but that'll be in the future. So let's look at some of the impacts here. The impact of adversarial perturbations can be quite profound. A significant drop in accuracy is one of the first consequences. This would make AI systems extremely unreliable and cause users to mistrust them. In safety-critical applications, these perturbations can introduce risks. For example, autonomous vehicles can misinterpret signs. When trust is eroded, users and stakeholders become hesitant to rely on AI. This would potentially stall its adoption. And vulnerabilities in these systems become a target for further exploitation. This was going to increase the risk of more security incidents in the future. So some real-world examples include altering images to cause misclassification, tampering with speech recognition systems to generate some incorrect transcripts, or subtly modifying the malware to evade detection. Mitigating the risks associated with adversarial perturbations involves a multi-layered approach. So here we're going to use adversarial training, where models are exposed to adversarial examples during training, strengthens and also to strengthen their resilience. Robust optimization techniques ensure that models can maintain their performance even under attack. Defensive distillation is another strategy where models are trained to reduce their sensitivity to small input changes. Input preprocessing can help neutralize perturbations before they reach the model, while anomaly detection systems monitor for unusual behaviors in real time. Ensemble methods will combine the outputs of multiple models to further enhance the security by reducing the chances of a successful attacks. So to wrap up, adversarial perturbations represent a significant threat to AI systems, with the potential to disrupt performance, compromise security, and undermine trust. These attacks leverage subtle input changes to manipulate the model's behavior, revealing that the vulnerabilities that exist even with the most advanced algorithms can be exploited. Mitigation strategies like adversarial training, robust optimization, input preprocessing are essential to safeguarding our AI systems from these threats. As we continue to advance our AI technologies, maintaining awareness of these risks and implementing effective defenses will be critical to building resilient and trustworthy applications.